Right. So this chapter is about experimental techniques in which we will be, see, you all don't go to a lab and no, not a lab means in your hands like going every day as a part. Lab being a curriculum of yours, if that is then very good, in which you have a assigned seat in the laboratory. Then and if somebody else is doing the experiment and you're just watching it, then that is not lab. Lab means you have your own bench and you have your set of apparatus. You have okay. So if that is there, then these things come very easy to you. So this is under your topic called alternative to practicals. So some part of the things is like story, but if you actually start applying your common sense, then things start falling in place. So this chapter will be grouped into three parts. First, we will see a little bit talk about some certain apparatus which we need. Apparatus or say devices. Imagine yourself in a laboratory right now with a basic knowledge of chemistry. Okay. The second will be, we'll know about what is known as separation techniques. Like how do we, today we'll be concentrating on devices, that is apparatus, and separation techniques. And after that, the third portion, which is the most important and the portion which you will get most confused, the qualitative analysis part. Qualitative analysis means this chapter will, see in chemistry we have got two parts, quantitative analysis, qualitative analysis. Quantitative analysis is when you are dealing with numbers, the chapter of stoichiometry. Quantitative analysis. Today, this chapter will be concentrating on qualitative analysis. Okay. So, how do you get to know which substance is what? Right? You have learned about, you have heard about so much about sodium, cadmium, potassium. How do you know this is sodium? Or something that I give you, whether it contains sodium or not? Or if I've given you something, whether that item is a pure item or if it is an impure item. These things are the questions that we are going to answer. But in today's class, we will not be addressing on qualitative part. We'll be addressing only on measurement as well as separation technique. Are we ready? Okay. So some of the macroscopic properties, you know, macroscopic and microscopic. Some of the macroscopic properties that you're going to measure in a lab will be volume, temperature, time, mass, density. They have not dealt with pressure, but in a lab, we also measure pressure. So to measure all these things, we have certain measuring instruments or devices, right? Or if they are not instrument or devices, we also call them apparatus. And apparatus can actually can have in its group a device and an instrument also. For example, if a little bit of engineering is involved, we call it as an instrument or a device, like a watch is a device or an instrument. Whereas a measuring cylinder, we don't call it an instrument or a device, we call it as an apparatus. But apparatus is overall a motherly word which can be used for all three categories, right? So our first category is measurement of time. Obviously in a lab, whether we are on a physics lab or we are in a chemistry lab, we will need to measure time. So time nowadays, earlier days we used to have stop clocks, analog ones. Now we have stopwatches, the digital stopwatches. And preferably in a lab, you should have a stopwatch which should be able to measure up to 1/100th of a second. Are you getting it? 1/100th of a second. That's the only thing that you should know. So you should know how a stopwatch works. I hope you know. In a stopwatch, you will have a start time, stop time, reset time again. Start, stop. Stop means how much did you clock? And again, you can have it on a reset. And then based on different brands, somebody will have 4 or 5 logs of memory into it. The more sugar you add, the more sweeter the thing becomes, the more costly. So then you can have the log to be taken out on a PDF device, or you can export it, you can plot it. Okay. Then comes measurement of temperature. The type of thermometers that we will be dealing for measurement of temperature in lab at this stage will all be alcohol in glass thermometer. So a thermometer is a device which has a glass tube with an internal core tube in which there is a fluid which will be sensitive to the rise in temperature. And the glass is graduated to a measurement scale. The measurement scale that we would be using is Celsius scale, right? And a Celsius scale works on the boiling point of water as well as the freezing point of water. What is the boiling point of water? 100 degrees Celsius. And freezing point is 0 degrees Celsius when the pressure is 1 atmosphere. And obviously, the substance that you're measuring should be pure water, right? Now, we do not use mercury in glass thermometer. The clinical thermometer that you get, don't go by the digital one. Clinical means the one that is to be read and again shaken, okay? That's a mercury in glass thermometer. We don't use it in lab because mercury, first of all, is very poisonous and it can spill out if it breaks. go and again destroy my experiments, other setups. So remember, if a 1 mark question comes, which type of thermometer do you use in a lab? We use an alcohol in glass thermometer. We don't use a mercury in glass thermometer. And the scale at which, as per your syllabus, the scale that we are following is the Celsius scale. And it is based on the steam point of water and the ice point of water. The steam point of water being 100 degrees Celsius and the ice point of water being 0 degrees Celsius, right? Then comes measurement of mass. Reference on mass and weight. So measurement of mass, we always use what is known as an electronic balance. Earlier days when electronic balance were not there, we used to use manual balance. Out here, they might ask you a question, what is the precision of an electronic balance? The precision of an electronic balance is any measurement device's precision means what is the lowest measurement that you can measure. It's not like that, not zero. How much is the lowest? Means say 0.1 gram. Can your machine differentiate between 0.5 gram and 1 gram? Yes. Can your machine differentiate between 0.55 and 0.60? Means 0.05 gram can it measure? That is known as the precision. Like if you go to say the airport check-in counters, so they generally measure in what? They measure in 100 grams, say 15.1, 15.2, 15.3. At an airport counter, you don't expect the measuring scale to measure something like 0.005. But if you go to a goldsmith or if you go to a jeweler's shop, then you will definitely find that 0.05 also matters or 0.01 also matters. That is known as the precision. And when you are using electronic measuring device, the first thing that you should also wait for is it to get into zero, steady zero. Because do you know how these machines work? They have got a device inside it which is known as the strain gauge. So once you put a, like next time when you go to a switch shop and he has got a digital scale, you can do a little bit of fun also. Till the person is getting the switch, just put your hand on the gauge and press it. You will see the counters are moving up. So there is a strain gauge. The moment you apply a force on it, it senses that force and then it reads it throws the data back on a logger. So you should be, if they ask you any sort of experiment, like you have done 7-mark question, they might ask you that you have used a device like an electronic balance. What are the precautions you need to take? So one of the precautions should be you should wait till the device is steady. Only after that you should measure. Somebody comes to your home with a digital spring balance, okay, digital spring balance, again the word is wrong, digital spring balance, and he wants to wait. So wait for it to get steady. Before that, even when you go to a fuel station, before pumping fuel into your car, the person will say sub-zero dekh lijiye. Register the machine to get to zero. So you should wait it to get it steady. Fine. Okay. Up till here, everything is easy. Then comes measurement of volume of liquids. Measurement of volume of liquids. So when we measure volume, okay, you know the difference between volume and capacity. Volume is the content of a liquid that you pour in a vessel, and capacity is the maximum volume that vessel can hold, right? So different, sorry for the spelling mistake, different apparatus we are using for different experiments. So one by one we will learn them. The first one pertains to your quantitative chemistry, stoichiometry classes. Titration. Okay, let's understand what is titration first, and then why are we studying titration out here? Because in titration we will be all interested to know about volume. Volume measurement is very important. So what type of device do we use? Okay, let's first understand what is titration as an experiment. So in titration, as I say, the simplest way to understand titration is acid-base titration, neutralization. So you will have one demon, Asur, and one Devta. Either you will know the strength of the Asur and you will fight the Devta with it to get to know what is the strength of the Devta, so that they neutralize each other, right? So what we do, we titrate one solution against the other, right? So one solution strength will be known to us and another solution's strength is not known to us. For us, the volume is more important of that, okay? And we will be titrating it. Now, question comes, how do we carry this experiment out? To carry this experiment out, we have two devices we use. One is a burette and one is a pipette. Pipette is something that you take in your mouth and you will be sucking inside that fluid. A pipette will be a very slender, small capillary with a bulb in the center and again one capillary on the other end. So the pipette is used, you put the pipette in your lips and you suck the fluid inside. Pipettes are generally 20 ml, 25 ml. So how the pipette looks like, the pipette will be a glass tube like this, which will be slender here and slender here, and a bulb, a thick bulb in between. So wherever there will be 25 centimeter, there will be a mark on the pipette. So usually you suck little bit more than the mark. And then we just hold the orifice of the pipette with our thumb. No, that's wrong. You should hold the orifice of the pipette with your index finger. This is not the correct procedure to do. You can't read it then properly. Okay, we hold it with our index finger, and then there is a mark out here, which shows that you should pipette, say, only 20 ml of oxalic acid. Or sorry, not oxalic acid, say you're pipetting some base. So when you're taking 20 ml, you're going to release this finger, and the excess liquid is going to drain out. And when the liquid level just coincides with the 25 ml mark, there will be only one single mark, one circle. You're supposed to hold it tight. Now question arises, how do I look at the pipette? Remember, when you are in a lab or any measuring device or anything, always the measuring device should be read parallelly to your eye level. Otherwise, you have a parallax issue. Like if you look at the watch right now, do you know what is parallax issue? Open your specs and close your one eye and look at the watch. And then close the other eye, you'll see the watch moving this way to that way. That thing does not happen when you keep it in between. So suppose the reading is somewhere between 6.1 and 6.2. Do you see it from this side? It looks 6.2. From its side, it looks 6.1. You should absolutely have it at your level. In fact, when you take your readings, when you do what you call labs, there will be a lab external who will be moving. He'll not be from your school. And the way you do your experiment, he will... Many children think that getting the right value is all about experiment. No. We are doing the experiment in a lab. We may not get the accurate value. What we should be more cautious about is how are we doing the experiment. In our days, there would be an external who would come and he would keep on noting something. He'll keep on roaming. So you're performing your experiment and say, suppose you're just taking the reading of the burette in this manner. 1 or 2 marks have already been cut. No matter even if you get a 38.1 as the right answer. No, you don't know how to use the apparatus. Are you getting it? Right. So in an acid-based titration, we will have a burette and a pipette. So have you understood what is a pipette? So question arises, sir, what do we take in? The usual practice is you don't suck in acid. So the acid will be always on a burette and the base will be on a pipette. So you take the 20 ml of that base whose strength is not known, and you will then take out the liquid and decant it on a conical flask or a normal beaker, acid base. If that particular reaction needs an indicator, then you will put 1 or 2 drops of indicator also on that. And then your acid will be on the burette. And the burette has got a small valve which you can keep on opening. At that time, we don't see the reading of the burette. You are not supposed to see the reading of the burette because you are neutralizing it. So when do you neutralize? Just understand the experiment. The conical flask has got acid in it, right? And what are you trying to pour? You're trying to pour KMnO4 on it. Say you're trying to, or say you're pouring acid on it and you've got a base out here. Now till the solution, and we have added a indicator in which it will be responding to a base. Say when it becomes basic, our solution colorless will become, say, pink, right? So you start opening your burette to some extent and you keep on shaking it. I'm not concerned about the reading of the burette right now. Then very gradually you should do, very gradually. Then at a certain point I will see pink just appeared. Pink just appeared. That means solution is just trying to go to, say, acidic. Solution is just trying to go to acidic, or say red just appeared. We have put methyl orange, okay? Red just appeared and again it has disappeared. Are you understanding? That means you are right at the fulcrum point. You had a base, you had an acid in your what you call conical flask. You had a base in your conical flask and you are dropping down acid on it. So you're trying to neutralize it. If you neutralize it, it should be neutral, neither acid nor base. So you find that when the acid comes down and if it becomes acidic, the indicator should show. So you get the first inch of red and again the red disappears. Means just aake bhi nahi aaya hai. At that time, you should be very cautious when you're doing these experiments. So then we again open it for one more drop, little bit. And then you'll find the last drop at which it just became red. and is no more going back to its color, that is that titration point. Stop the burette and now see at what level the liquid has come. If the liquid is at a higher level, get up on a stool and then read it. And when we read it, okay, when you read it in a device, it will be something like this. See, this diagram also they may give you. We call it the meniscus of the, you can have a concave meniscus, you can have a convex meniscus also. Understood? Question is, what reading do I take? You always take this reading. Okay. You don't take this reading. You don't take this reading. You take this reading. Say this was 35.5, so 35.5. At that time, your eye should be always in line with it. So solution, whichever is in the burette, is known as the titrant. We call it as the titrant. Have you understood about titration? Nobody will ask you, see, the end of the day, they will ask you what is the burette reading. This will be a part of a question. They will not ask you like what was titrated. The question will come, so and so was titrated against so and so, this many molar, this strength, and they'll say what are the precautions you should take. So burette reading should be always read with eye level. Pipette reading should always be read with eye level. Otherwise, your experiment is wrong at the very first stage itself. The two solutions which you're trying to titrate, they will give you in two beakers. But you are supposed to take only 25 ml or 20 ml in a pipette. So when you take 20 ml in a pipette, make sure that all the measuring technique, pipette should be held with the index finger. Pipette's measurement should be read on the same axis and line and the same level as that of your eye. And then proper indicator should be used, and the burette valve should also be tight. Generally in labs, the burette valves are never tight. So it keeps on tapak, tapak. So if you don't get a good burette, at that time you should also have rubber bands or something so that you can just fix and keep it handy. Understood? So this is one type of volume measurement where we are using burette and pipette. This type of measurement will actually use the unit centimeter cube. Anyone has any confusion with unit conversions? Centimeter cube, right? This will have units as centimeter cube. Let's see the next type. The next type is a measuring cylinder. Measuring cylinders are also known as mixing or graduated cylinder. Measuring cylinder is a cylinder of uniform diameter with a flat base. So a measuring cylinder can measure in centimeter cube, and some measuring cylinders also measure in milliliters. So here comes a confusion between us that, sir, what is the difference between centimeters and liters? So let's understand this. Volume, if you have any doubt, usually measured in meter cube, but in lab we will be using much more smaller units. Okay, so another is volume can be also measured in liters, and volume can also be measured in centimeter cube. First, let us understand what is a liter. A liter is the volume of a cube whose edge is 1 dm cube. Sorry, 1 dm. A liter is the volume of a cube whose edge is 1 dm. So let's see what is 1 liter. 1 liter is equal to the volume of a cube whose edge is 1 dm. So it should be 1 dm into 1 dm into 1 dm. What does dm means? dm means decimeter. So each decimeter is same as 10 centimeter. Agreed? 10 centimeter into 10 centimeter. So a liter is 1000 centimeter cube. This is 1 liter. Which gives me that if I measure in milliliter, it should be 1 centimeter cube. 1 milliliter is 1 centimeter cube. 1 milliliter means liter divided by 1000. This one also divided by 1000. Is this clear or not? Liter is the volume of a cube whose edge is 1 dm. Agreed? Okay, let's also see one more conversion. 1 meter cube stands for what? 1 meter, 1 meter, 1 meter. Each meter is 100 centimeter, 100 centimeter, 100 centimeter, which gives me 10 to the power 6 centimeter cube, which is 10 to the power 3 into 1000 centimeter cube, which is 10 to the power 3 liters, which is equal to 1000 liters. It means if you go to a shop, garment shop or a clothes shop, and you get that meter stick, if you've seen that meter stick with which they measure the fabric, so that is 1 meter. Imagine a cube of that edge. So that cube's volume is 1 meter cube. Inside it, we can actually load 1000 those water bottles. Each of those water bottle is 1 liter. So you should be able to decant 1000 bottles of those into a cube, which is manufactured with the stick that you see in a fabric shop. Correct, na? 1 meter cube is 1000 liters. 1 liter is 1000 centimeter cube. 1 cm cube is 1 ml. Perfect. Clear? Okay, so we go back to our measuring cylinder. So I think now these are clear to you. What is 1 centimeter cube? This is what I was saying, that your measurement should always be, these type of drawings may come, which is the appropriate drawing. 2 drawings that so and so, Sarah is watching like this and Anna is watching like that, to which is who is correct. So if that type of question comes, always the bottom one. This is the meniscus and the eye should be at the same level. No parallel axis created. Clear? Okay. Measurement of volume of gases. Now say we have a reaction in which gas is being produced. So in that case, we measure the volume using a syringe. Syringe is the syringe, the pharmaceutical type of syringe that we have seen. So a syringe always has a plunger. When the gas is produced, the gas will create a pressure in which the gas will be moving the plunger. So amount of distance moved by the plunger is recorded, and that way you get to know how much volume of gas has been formed. So if you go to a pharmacy, what is the standard size of syringe that you see? 5 ml. Also you see 1 ml and 3 ml. These are the 3 standard sizes. Sometimes if you see for higher grades of injections that they use, 10 ml syringes are also there, but usually 5 ml, 1 ml and 3 ml. These 3 are the standard sizes. When you go to rate of a reaction, in that chapter we'll have a chapter on chemical kinetics also. Okay, rates of a reaction. At that time, how fast a gas is being formed, that also is tells me about the rate of a reaction, whether the reaction is proceeding fast or. So rate of a reaction means, how do you know that the reaction is going fast? The reaction goes fast if the reactants are consumed in a quick manner or the products are formed in a quick manner. So if gas is one of the product, the rate at which the gas is being formed gives you also an indicator whether the reaction is fast or whether the reaction is slow. Say suppose the reaction is slow and you add certain catalyst to it and you find that the plunger starts moving very quickly. That means the reaction has been expedited with the use of a catalyst. So the questions from this chapter won't come as a single question of 7 marks. There will be questions from the existing chapters where these things will be embedded. Stoichiometry में एक तो घुसेगा ही यहाँ में से. Volume clear? So we see here, we saw in our syllabus, we see volume in forms of titration, burette and pipette. Then you saw volume in terms of measuring cylinder, and you also saw volume of gas formed, how we measure for volume. So this is done. Our next topic is all about separating mixtures, right? So let's understand what type of mixture. Now separating mixture, horses for courses. You do not have one technique which you will apply. So we were going to see which separation method to be used depends on what is the mixture and what is the property of the substance. It also depends upon whether the substance to be separated are solid, liquid or gas. Say for example, I have mixed sugar in water, solid in water. What do you want? Are you looking for the water or are you looking for the sugar? So based on all these 4 criteria, we have divided the criteria and then we're going to analyze one after the other. Okay, solid and liquid mixtures, the most common. Solid and liquid mixtures are categorized under 2 heads: solubility and insolubility. If you are soluble, your headache is much more. If you are insoluble, the headache is not much more. Okay, you take some marbles and you put it in a glass of water and I ask you, separate the marbles and water. It's a kiddo's game. So the first thing that we're going to see is based on insolubility. Let's say you have got sand and water, and one of the solute. You should also understand what is a solute, a solvent and a solution. So if you have what you call, wait, hold for it. let us not go by the definition. Let me give you in an understanding manner. Solute and solvent. Very easy for us to say that if sugar is dissolved in water, sugar is the solute and water is the solvent. Okay. Now understand in the most rugged manner. Two ways to understand. One is, if it is a solid and a liquid, the solid, generally people think that it is the solute. No, it's not like that. The one which is more in count is known as the solvent, and the one which is less is known as the solute, right? So let's say that at a glass of water, I am adding 1 teaspoon of sugar. Now sugar is the solute, water is the solvent, and to a sack of sugar, with the syringe, I am pouring water inside it. Now water is the solute, sugar is the solvent. Other way to see it is that, look into the final state of the solution. So in the previous example, what did I say? In a glass of water, I added sugar. What is the final state of the solution? Liquid. Now look at the two participants for their states. I had water and I had sugar. Water was liquid, sugar was solid. Whoever state matches with the final state, that will be known as the solvent. Water was liquid, the solution is also liquid. So water is solvent, ye zyada matra mein tha, and the solute got dispersed in it. Now go to the experiment of the sack of sugar. I have a pile of sugar on the floor and I took 1 syringe of water, and like a kiddo, what I did, I just emptied the syringe into that pile of sugar. What is the end state of the mixture? Solid. Who came as solid? Sugar came as sugar is the solvent. Have you understood? So let's see, it says a solvent is a substance that dissolves a solute. People usually think dissolves a solid. You read it with your mentality, let's solid. No, no. A solvent is a substance that dissolves a solute. And let's go by our next example. The sugar, pile of sugar was the substance that dissolved the syringe of water. So the pile of sugar was my solvent. And what was solute? The water was solute. The glass of water dissolved the teaspoon of sugar. So the glass of water was my solvent. Okay. A solute is a substance that is dissolved in a solid. Generally, the word is solute. So what comes in our mind is solid. No, it's not like that. Right. And a solution is a liquid mixture composed of 2 or more. Generally, if it is a 2 component, we call it a binary solution. And if it is more than 2, then it becomes a tertiary solution, or maybe more. So usually we deal with binary solutions itself. So out here, what we are dealing with the cases where the solute, whatever you have put, it's not mixing into it. So it's no question of solubility out here. So if they are insoluble, then one of the mode is filtration. Now, when do you use filtration? We use filtration when one component easily settles down, like sand and water. Sand is going to easily settle down. You keep it for some time, the sand will settle down. And then you use a filter paper and you just pour your content. Whatever has come out is known as the filtrate, the way you make tea every morning. When you strain tea, that is known as a filtrate. And whatever is left is known as the residue. Okay? Now, it is not that residue is impurity or filtrate is impurity. It depends upon what is your quest. If you are looking for not the tea, but you want the tea leaves only to put on the rose plant in your flower tub, then the residue is more important for you. Clear? Okay. The next one is known as decanting. All of us do that. Lots of vegetables, and we have soaked them after cutting. After chopping the vegetables, we have soaked them in a bowl of water. And now you want the water. So what do? You just strain it through, decant it. When the solid does not mix with the liquid and you want to either separate the solid or the liquid, then you can just decant it. When they are quite large, then this is also known as decantation. Important for our understanding is centrifuging. Centrifuging is the case in which the solute particles are so small that they will not actually, settle down even after kept for some time. They are not going to settle down. They are mixed evenly into the solvent or the solution. The solution is evenly, but in that solution, there is like, I can't call it a solution, so I will call it either as a suspension, very good type of suspension, or a colloid. We'll say it's a colloid. Okay. Now, what do we do in that case? We will use a centrifuge. A centrifuge works on the principle of centrifugal force, which is mv square by r. More is the mass, more is the centrifugal force. So everything that is heavy is going to get unsettled at the base. This is done for blood sampling. Whenever they take you, like they'll say that go for a blood test, but make sure you're testing it from your plasma and blood cells. So blood has blood cells and blood plasma. So they will take out blood, they will put it in small ampules, and the ampules will be put in a centrifuge, and they'll centrifuge it. Once they centrifuge it, the blood cells will all go in this part, and the plasma will separate out for some time. Then what do? This decant out the plasma. Have you understood? Yeah. Platelets and plasma donations also happen during people suffering from malarias and other things. So at that time, whoever goes for blood donation, he doesn't have pain, but his whole day will go away. First of all, they'll take out blood from your body, then separate, take your platelets, and again transfuse your blood back to you. So first you'll donate blood, then you'll take blood. So your whole day is almost gone in the hospital. तुम कमजोर नहीं बन जाओगे? We don't need your entire blood, na? We can't throw it also. You will form, you're a normal person, you will form your platelets again. So we call a normal person as a normochromic. You will build up your platelets very soon. And if you're suffering from dengue, not actually malaria, dengue, then I need blood platelets, and your platelets match with me. So you will first donate your blood, from which the platelets will be separated. That is what I will take. And rest is again put in your body. We can put it in a packet and allow you to sip through it, okay? So the pure liquid can be decanted after the solid has been forced to the bottom. The solid has been forced to the bottom. This method of separation is used extensively to separate blood cells from blood plasma. The solid particles of the blood plasma cells are flung to the bottom of the tube. The blood cells will come here and the plasma will remain on top. This is known as centrifuging. Clear? Okay. All these three pertain to the condition when they are not soluble. So we're going to see something about when solubility is there. Solids and liquid mixture based on solubility. So filtration we have seen, decanting we have seen, centrifuging we have seen. Now let's come to evaporation. Salt water, the best example. If you are interested in salt, then evaporate the water. Here the game we will be playing is based on the difference in the boiling point of the two substances. However, if you would have been interested on the water, then what do? You have to go for distillation, simple distillation, right? So evaporation is understood. Crystallization, this actually if you do in lab is very interesting. In crystallization, what do we do? In crystallization, I'll come to filtration also, okay? In crystallization, okay, filtration is done, sorry. Crystallization, we will be taking what you call a saturated solution. Do you understand what is saturated solution? Let's take a cup of water and let's start adding sugar on it. 1 teaspoon and stir it. 2nd teaspoon, 3rd teaspoon, 4th, 5th, 6th. After some time you will see that if you add any more sugar in it, the sugar is no more dissolving. But there is a catch. Now you are no more allowed to stir it, because every time you stir it, what are you doing? You are increasing the temperature. So if you increase the temperature, the kinetic energy of the particles increase, and again gaps will be created. So new sugar particles can come and fill those gaps. So what we are doing, we are not allowed to stir it, nor you are allowed to increase the volume, nor you are allowed to raise the temperature. So saturated solution means a solution. My brain is saturated, means I can't take any more. A solution is said to be saturated when you cannot mix further solute in it just by adding into it. And when we define solubility, solubility is defined for a particular temperature. If every different temperature, the solubility will change. Okay, sugar is no more dissolving. Start heating it, again the sugar will dissolve. No, so we can't heat it. How many of you have seen the practice of making, you know, what is called, what do we call it in English? There's a chashni jisko bolte hain. Sugar crystals. What is it called in English? I'm not getting the word. Butterscotch ice cream. If you have butterscotch ice cream, don't you get that the sugar crunches which you can chew? The chashni that we make. Okay, so how do you make it? So what do? We will take a lot of sugar in a pan. It's very easy to make. Take a lot of sugar in a pan and add some water. Don't add a lot of water, and start heating it and put some more sugar and make it caramel is the word. Okay, caramel. So you make it absolutely thick. And after some time, just allow it to cool. When it cools down, after you have made butterscotch ice cream, you need to have that caramel feel in it. So, and you spread it on the what you call frying pan. Once it cools down, and suppose if you spread it like the shape of an octopus, the entire octopus like shape will come up. Now what do? You put it in a mixer grinder with just not rough bricks and just churn it once or twice, not more than that. 1 or 2 whips. You don't want it to be powdered. You want the chunks to be filled. And then you just mix it on your ice cream slurry before putting it into refrigeration. So it will give you that butterscotch wala feeling, right? So how do we do crystallization in a lab? In lab, we used to have these experiments, and here you will be scored based on how nice crystals you can make. So we used to make saturated solutions of a particular salt, say copper sulfate crystal. So copper sulfate's aqueous saturated solution will be made, and you will be heating that solution to make sure that now the solution is absolutely saturated. And then after we have made that hot copper sulfate will be poured in crucibles, and your roll numbers will be written and the crucibles will be kept. After 2 or 3 hours, they will form beautiful crystals. Whoever crystals come in large big things, the scoring is done in that manner. So the question comes, sir, why did my crystals didn't come out good? Because you were in a hurry, you did not expel out all the water. So water should all be expelled out. That's also known as crystallization. That means everything is gone, and what I am now remaining with is only with the salt. Understood? Yeah. Then simple distillation. Simple distillation is this process. This is reverse. Like say, reverse of, I'll not say reverse. This is like evaporation is when I'm more interested on the residue. Distillation when I'm interested in the water. Salt and water, I'm interested in water. So what do? I start heating it, and every water that evaporates goes through a condenser and it's collected on the other side. So this is known as distillation. Salt will remain on this side, water will come on this side. Okay. Liquid mixture. Liquid mixture, there are 2 types of mixtures, miscible and immiscible. If you are immiscible, like say oil and water, and you have got 2 colored fragments, then you will see. So what we use is a separating funnel. Separating funnels are very crude way of separating. So what we will do, we will separate it till the moment we are able to see exact blue. Separate that, right? There will be loss of liquid in this case. Then take this beaker away. So this is pure blue component. Then allow it to drain down through the line of control and allow the red to come, and you ensure that complete red is getting decanted. Now stop it. Now whatever you are left with is red, then collect the red in another beaker. But there will be loss. Beach wala kahan jayega? Stop it. No, not loss. See, not exactly stopping. You can't decant it from here. So you want pure blue. So you will be stopping it somewhere at here. Right? And then you will drain out this much of blue, the border, and little bit of red also you will drain out to make sure that now everything that is coming out is red. Yeah. And then you take the red out. Sometimes you might have something where it's 2 miscibles with a solid inside. What will you do in that case? 2 miscibles and a solid inside. So in 2 immiscible. So if in 2 immiscible you take out 1, so first we have to take out the solid out. So first try to take the solid out by filtration if it is possible, and then you use your separating technique. Oil and water is one of the best example. Right? Liquid mixture, immiscible, we are using separating funnel. And suppose you are having miscible liquids. In miscible liquids, we use fractional distillation. Have you read about fractional distillation in grade 8? Fractional distillation is a procedure in which we are able to distill out various components based on the difference in their boiling point. The best example is crude oil. Crude oil has got so many fragments, right? It will start with, say, petrol, then you have naphtha, then you have diesel, then you have got kerosene, aviation turbine fuel, furnace oil. So what do? You heat crude oil and you pass it through a fractional column, and you distill the vapors at different temperatures to get those components out. Even air separation, that's where that photo was given. Air separation, when you separate air and you do fractional distillation of air, you're going to get what? Nitrogen, you're going to get oxygen, and you're going to get argon. So nitrogen is present in abundance. That's why nitrogen is the cheapest gas when air column fractionation happens, because all the raw material is air which God has given you free of cost. So what is the raw material? Power is the raw material. Electricity is the raw material in this, because the compressors have to run, they have to compress the gas, cool the gas, and then they have to expand it. So first nitrogen will come out. After that, oxygen comes out, and then argon comes out. So argon is very costly because it's very less in the atmosphere. Okay? So that also happens through fractional distillation. So the column that we use is known as a fractionating column. So you will heat it, and then at a particular temperature, this is a very simple setup, but the better setup is crude oil. Did you understand how we separate fragments from crude oil? Crude oil has got refining of crude oil is a process in which we use fractional distillation. The crude oil is going to have a lot of components inside it. So when you have crude oil, you first heat crude oil and pass it through a fractionating column, petroleum. Obviously, the crude oil has been cleaned and done. So first of all the rich gases will go out. After that starts your petrol, naphtha, diesel, aviation turbine fuel, kerosene, furnace oil, and at last whatever is left is known as bitumen, which we use for making the road surface metal. Yeah, that's the black tar that is left. So fractional distillation, if you Google also, you will see there's a fractional column, and every column is giving you different products.
Why the last graph inside
Which one? Fractionating column with short lengths of grass rod inside to increase the surface area. Surface area means, see, a reaction will proceed faster when there is more surface area to it. Surface area means, okay, take out a chip of wood and take a block of cube. Which one burns faster? The chip burns faster because the chip has more surface area as compared to the area of the block. So for a reaction to go fast, the collisions have to happen quickly. That you will read in chemical reactions later on, kinetics. So in that, we have to increase more surface area. So glass rods are given, which will be increasing the surface area. Right. This is the only one where you'll get questions based on slight numericals. Chromatography. Chromatography is a technique which is used a lot in forensics as well as also in pathology also. Okay, as well as clinical pathology also use chromatography. Then a lot of organic chemistry study happens, and it is also the base of what is known as forensics. So let's understand what is chromatography. Chromatography is used not only for solid that are soluble, can also be used for liquid. Let's first understand what happens in chromatography for solid. Let's try to understand first. You will have a paper, a typical type of paper which is called a chromatography paper. That's just like a post-it sort of a strip. Okay, so what we do in chromatography is that you can use a filter paper also. Like we have done chromatography using filter papers. For example, the experiments that we did in our school days, we used to take carrot juice and we used to see what are the different fragments or components inside carrot juice. So you used to have chlorophyll, xanthophyll. So all those have to separate out. Now how that separation happens, take a paper strip or the chromatography paper strip, and first you just mark a line with a pencil. Don't use pen because the ink is going to get damaged when the chromatography process starts. So just mark a pencil point and give a drop of that particular mixture from where you want to separate out the components. So in our case, we used to have a filter paper and we used to use a Johnson's bud. We used to dip it in carrot juice and keep on putting concentrated carrot juice out here. Okay. Now, after that, the process is simple. We will allow a solvent to pass through it. The solvent will actually drag the components along with it. Each component will have two types of properties. One is absorption by this particular chromatography paper. Another is how does it proceed when this particular fragment is trying to take it away, or that solvent is trying to take it away. The solvent used is usually ether. Ether means methylated spirit sort of a thing. So what we will do now, we will take this particular strip and we will dip the portion below this mark into this solution, that is the solvent. Now the solvent is soaked and the solvent starts climbing up. As the solvent starts climbing up, there are 2-3 products out here. it starts dragging them along. Each product will have a different, what you say, it will react differently to the drag force created by the solvent, as well as each product will be absorbed differently by the chromatogram paper. Some will show adhesion, some will go away, and that way we actually find and we are able to separate out one or two more components. Inkjet printer ink also, if you, the colored printer ink which is there, if you try to put it on a chromatogram, it will just give you all the colors that will come out of it. Is this thing understood? Suppose there is a mixture of dye, that mixture of dye is kept here. After the solvent has completely gone up, make sure that the solvent, this thing, what you call this, does not touch this mark. It should touch only the bottom portion of the chromatogram paper. And then the solvent will slowly absorb and go up. As it goes up, it will drag and take it away. Clear? And we always cover the lid so that the solvent doesn't dry. The solvent is very volatile. It has to be volatile, otherwise it will not absorb. Petrol can also be used, ether can also be used, nail polish remover can also be used. The job is that it should climb up. So these three dyes are coming out. So they separate because the substances have different solubilities in the solvent and are absorbed to different degrees by the chromatogram paper. As a result, they get separated. Now this is one way to get to know what was present. How many components were present? This is very simple, kiddo's job. Our next job should be that we are on a crime scene and we found something and we need to know what is this particular item. What is this particular item? Yes or no, right? So for that, what we do, we have to understand something which is known as retardation factor. Okay, let's answer this question. Before looking at this question also, it says that we have done 3 samples of chromatography. Okay, sample 1, sample 2, sample 3, sample 4. Which one is a pure substance? A pure substance has only one type of particles. So I think B is a pure substance. And C is also a pure substance because you don't see any other pigmentation other than them. But this is a mixture. This is a mixture.
Yeah.
Have you understood? Very easy. This is the kiddo part of chromatography. The interesting part is this, retardation factor. So what is retardation factor? Now, we will see 2 things, the distance moved by the solvent and the distance moved by the solute. So once you have made your pencil mark, after that what we will do, we will see how much distance did my solute move. Clear? And you will also measure how much distance did the solvent move. The solvent started to move right from the start of the paper. And then you take out that ratio. That ratio is known as what? RF, retardation factor. A good lab, a good accredited lab will have RF factors of all good chemical reagents, agents, fluids that are known to us, like blood or say serums, everything they will keep it. Now, if you think that there is a new type of a chemical which you diagnose that you don't know what it is, so you will carry out 3 or 4 tests. That's no doubt about that. You can also do a chromatography and see what is the RF factor. If the RF factor matches, you can say, oh look, starch was present. This is starch. So there is a complete database of RF factors measured. If you see CSI episodes, then this RF factor is discussed a lot. CSI, you know, Crime Scene International, the CSI Miami, the CSI seasons, if you see. So in those CSI documentaries, they will be speaking a lot about this. Acha. There might also be some liquids in which a liquid is completely miscible in a liquid and they are both colorless. That is more interesting. Out here, when you are doing a chromatography, you are seeing 2 different components in 2 different colors. Now say I have got my liquid which has got only one color. Solute has also, there you can use even ultraviolet rays. If you have interest in seeing, crime documentaries, then they will show you how forensic people with their ultraviolet rays on the chromatogram, then they put the ultraviolet ray on the chromatogram sheet and it will show 2 or 3 different components. So on this we get some problems also, right? And those agents, or you can have ultraviolet or you spray something which is known as a locating agent. Locating agent is another reagent. You can just spray it on the chromatogram paper, then whichever things were colorless, they will all show their colors. So look, you get locations. So we get experiment, like let's see this problem. The following values were obtained for the chromatogram produced for amino acid glycine. Distance traveled by glycine is 2.5. Distance traveled by the solvent is 10. Solvent will always travel more distance. So calculate the RF factor. RF factor is 0.25. So RF values are cataloged in a data book for a vast array of substances. So RF values of unknown substances can be compared with the values of a data book to identify the known substance. Like the glycine will always show an RF factor of 2.5. Tomorrow, if you are doing a test in which glycine may be present or not, be very specific to it. 2.5 may be for many other reagents also. But if you are testing for glycine and at that time you find 2.5, this is one sort of a indicator, yes, this can be. Then do 2 or 3 more confirmatory tests and you should be able to decode it. Our next section, on the last for today, is about criteria for purity. Pure substances. So what is a pure substance? A pure substance contains only one type of particle. In our language of chemistry, anything that is pure means it should be either an element or a compound. Is this thing clear with you? So your book has something very nice written on it. It says, pure apple juice does not mean pure in chemistry. That's pure in terms of everyday, day-to-day life, behavioral English, that's correct. But in chemistry, apple juice is not a compound, it's a substance. Okay. Now the criteria of purity comes down into 3 sections. The first is known as melting point. Now when you're talking about melting point, take the word as solid. What did you understand for melting? Melting is a continuous temperature process. So if you are a pure solid, you will have a sharp melting point, and if you are of an impurity, then your melting point will have a range. Sometimes it may melt at this temperature, sometimes at the other. If you are a pure liquid, then the temperature will remain steady at the boiling point. Why does the temperature remain steady at boiling point? Can anyone answer to me? That I know, but why does it? Melting, boiling will be said to be complete when 100% of the liquid converts to 100% of gas. So boiling starts when the first component has become gas, boiling has started. Temperature is locked at 100, say for water. Now it will remain at 100 till all the water molecules have converted from liquid to gas. So that timeline is actually known as the steady point of melting point. It's pure. Okay. Same will be seen even in freezing also. Same thing, yeah. And next comes is chromatography. Can you tell me without looking at it, in chromatography, how will I know it's a pure substance? One impression. So it says, if the pure substance will produce only one well-defined spot for a chromatogram. If impurities are present, then several spots will be seen. This part of the chapter is quite easy till now. Next part of the chapter is not that it is difficult. Next part of the chapter needs interest from your side also to know. It's like it will be like how a child starts learning colors. One child in the class may keep on saying, no, this is blue. He will say, no, this is light blue. This is deep blue. This is Prussian blue. This is indigo blue. So more you have love for science, chemistry, the second part will get easier. Otherwise, the only solution you will have is make charts of it and start mugging it up before your exam.